Today, we will be talking about optical instruments, things we use to help us see things. And so these optical instruments usually involve multiple lenses and or mirrors. But the first one we're going to talk about is the simple magnifier, a simple single lens. So a simple magnifier is a lens we use to allow us to see something better. Now, how do we see something better? We want it to be bigger, right? And when you're looking at something with your eye, you probably don't even think about this, but the way you measure size is by how big of the angle it makes with your eyeball. So if I take my pen and I hold it out here arm's length, it doesn't look the same size as if I bring it here. Right here, it fills up my entire range of vertical view. Out here, it's a small portion of it. Now, of course, my brain knows what its position is, and so it easily determines, okay, no, it's really the same size, it's just closer and farther. But with things like, let's say, the moon, there's a very common misconception about the moon's size. Because when the moon's up in the sky, you see it without reference to anything else that you know its size. And then when it comes down the horizon, you see it with reference to things that you know their size. And your brain tells you, oh, it must have changed size because I have a reference here and I didn't have a reference there. So if you don't have a reference, you really don't have a way to determine anything except for the angle that it took up with your eye. And so when we're talking about magnification, and specifically angular magnification, because we can't talk about transverse magnification, that's not for what we're looking at, but for just the relative sizes of object and image. So with the eye, we measure the angular magnification, how big the angle was made. So angular magnification, here's my picture. You bring it closer, it makes a bigger angle with the eye. And unfortunately, I seem to have skipped my first clicker question. These are all saying the same thing. A magnifying glass is a single lens that is used to get an angular magnification. So here's the definition of that angular magnification. Look, I went through 5 slides, 2 minutes, because there wasn't really much except for one thing on there. This is what a magnifier is. So it's the angle that the object would make if it was viewed with the unaided eye. That is just your eyeball looks at the object. What angle does it make? Divided by the angle that it makes, or I put that backwards. Put it backward. It's the angle it makes with your magnifier divided by the angle it would have made by itself, unaided by itself. So that's the angular magnification. Hopefully, if the next slide's not our clicker question, I completely forgot. Oh, good. There it is. So our first clicker question, what do you naturally do when you want to see something in greater detail? Like if you want to read the fine print on a contract, what do you do with that contract? Do you move it closer to your eye? Do you move it farther from your eye? Do you increase the light? Do you decrease the light? Blink rapidly or stop blinking? Okay, everyone's answered. And we had 19 that moved it closer to their eyes and 2 that increased the ambient light. Now, in terms of answers, there are wrong answers, but neither of these are wrong answers. These are both right answers. Just so everybody feels confident when I call on you. One of the 2 people that said increase the ambient light. Why did you say that? Jordan?
Because if it's too dark, I can't see it. So I try to lighten it up so I can see it.
Okay, so you brighten up the light because if it's too dark, you don't have enough contrast to see fine detail. Okay, so that's a good answer. It's a good thing to do. I did that this morning. Okay? Somebody who was in the 19, why would you move it closer?
It makes the print look bigger.
Okay, it makes the print look bigger. Now, when you become my age, you actually go with a third option that works even better. You take out your iPhone, you triple click to get to the magnifier, and you use that. Because then you can magnify and read on your phone, right? None of you are my age, so you don't do it that way. I'm not sure how blinking would help you. Not blinking would probably be a problem because then your eye would start, being uncomfortable. But these 2 here were both good answers. We're going to focus on the one that 19 people said, to move it closer. So to get the biggest angle that you could get with just the naked eye. You'd bring it as close as you can focus. What do we call the closest distance that you can focus on? Near point. So you bring the object up to the near point. So here we go. So if you bring it to the near point, then you're going to have an angle. And notice, just like when we talked about making the diagrams for constructing an image from an object in a lens or an object in a mirror, we make this principal axis, and we put our object just sitting up from that principal axis. So if it's at the near point and it has a height h, then how would I find this angle? What trigonometric function relates opposite and adjacent? Tangent. So I know it's written there, but I'm just going to hide that. So we have tangent of theta is equal to the height of my object divided by the near point, the distance, the closest distance I can put it to my eyeball. But that's tangent theta. Now comes the obvious answer to a non-obvious question. Why would you bring something closer to your eye to examine it again? Because it makes it bigger because it's really small, right? If it's big, you don't bring it up closer to see the fine detail because you already can see the detail. It's only if you're looking for that fine detail for a small feature that you'd bring it closer. So even if I have something that's big like this pen, if I'm trying to read something that's in micro printing on it, I bring it up and my object is just that micro printing. So if that's the case, if it's a tiny little object, then it's always going to be a small angle. Establishing that it's a small angle is important, so that's why I spent, another one of our minutes on that. For small angles, we had that sine of theta is approximately equal to theta. We used that last semester, didn't we? When we talked about pendula. So sine theta is approximately equal to theta for a small angle. And cosine of theta is approximately equal to 1 minus theta squared. So if we take that and we make tangent theta, what is tangent theta equal to in terms of sine and cosine? Sine over cosine. We would have that for small angles. But if an angle is small, the reason we put 1 minus theta squared was so we had a dependence on theta. But if theta is small, I'm going to have theta over 1 minus theta squared. The difference between 1 and 1 minus theta squared for small theta is going to be negligible. And so that's approximately equal to just theta. So for small angles, sine theta is approximately equal to theta, is approximately equal to tangent theta. So my magnification or my tangent theta, I can then write is approximately equal to theta. These mean the same thing, the wavy equal sign and equal sign with the tilde over it. So this is my unaided eye. Okay, that didn't quite fit. So the angle, the largest angle I can make something with the unaided eye is going to be the height of the object divided by the near point of my eye. Now, because I've already used her as an example, and we know that Gila's near point is around 9 inches. And if somebody has normal vision, their near point's about 25 inches. Who can see the fine detail better? Somebody with normal vision or Gila? Gila can, because she can focus on it when it's closer, hence she can focus where it makes a bigger angle. So depending on your profession, being nearsighted might be beneficial, right? Because you can focus on nearer things. So there's our angle for the unaided viewing. Now we're going to put a magnifier in. So we're going to take this picture and modify it by putting a lens right there. We're going to basically say the lens is right next to the eyeball. It makes our lives simpler if we say that. If we move the lens away, it changes the math a little. We don't need to complicate things. So if I put that lens there, what's going to happen? Okay, it's going to focus the light. Now, there are two options on how it's going to do it. If I have the object farther away than one focal length, where's the light going to come to a focus? That's the other answer. It's going to be behind it. Let me draw the pictures to go with this. So here's my lens. There's my, okay. I know when we did this in class, I got F and F prime different in my different pictures, which didn't help my credibility at all. So if I put my object beyond one focal length away, when I did my diagram, excellent. Okay, straight line. When I did my diagram, it gave me an image, and that's only two of the three rays. What are the names of the two rays I just showed? Parallel ray is the first one. The second one is supposed to be going through the center of the lens. What do we call that? The vertex, I think I heard somebody say. What's the third ray that I didn't show? Center ray we can only use with a mirror. The focal ray. So the focal ray would go through the focal point here and then come out parallel. And of course, my picture was horribly bad because I wasn't using a ruler or anything. That's why when it comes test time, you'll need to use a ruler. I'm going to be grading on the accuracy of your three rays. But my image would be on the opposite side. Now, if we had that occurrence here, if the image is being formed back here, I can't focus on that image, right? You can only focus on things that are farther away than your near point. If it's on this side of the lens, so it's inside your head or behind your head, you can't focus on it. So that is not going to work for a simple magnifier for us. Where do I need the image to be formed for me to be able to focus on it? It needs to be in front of my eye. In fact, the closest it could be would be at my near point. And so what I'm going to do is I'm going to put this lens here and have the distance, instead of the object here, it'll be the image at the near point, and the object will be somewhere closer, like let's say here. Now I've got a picture to go with that, but I want to start with the unaided eye and see how it's different. The object is closer. What's that going to do to the angle? Okay, I made my object fit that, but the object should be the same height. If the object's the same height, what does that do to the angle that this makes? Yeah, the vertex ray is going to be a much bigger angle, which means it's going to look bigger to me. That's our goal. That image I'm going to view looks like a much bigger angle because the image is going to be formed out there. So I have a picture drawn here showing the situation. Now, this is a different situation than what I just showed. I said the closest we can have it is at the focal point. Or not the focal point, at the near point. This picture shows the image at what location? It says, virtual image formed at infinity. Why would you choose to do that? Well, if you make the virtual image formed at infinity, then the eyeball can be relaxed because accommodation is adjusting the focus away from the far point to something closer. So that infinity means it's your ideal far point. If you're nearsighted and not wearing your spectacles, then you actually would adjust it so it's not at infinity, but at your actual far point. Because your actual far point, your eyeball is relaxed. Why is that important? If you're using this for a long time and you're constantly having to use maximum accommodation, your eye gets tired. You have eye strain. And so since we're using a device to magnify, and that device can do a lot more magnification than the small amount of magnification I get by accommodation, we generally do the calculations for a relaxed eyeball looking at something infinitely far away. So that's why this starts with that. It's also simpler math. I'm going to do the other calculation after I do this one. So now I have an object that's at the focal length away, so the image is infinitely far away. The vertex ray goes straight through, so the image is going to be on the same line as this vertex ray. So that means my aided angle is the angle between that vertex ray and my principal axis. Well, once again, using geometry, I have the opposite side is still the height of my object. The adjacent side is now the focal length. And so I have tangent of theta is equal to h naught over f. But because it's a small angle again, I can just say that's approximately equal to, wow, my handwriting today is even better than normal. And then we finally just calculate the magnification. The angular magnification is equal to theta aided over theta unaided. So theta aided, that's what we have on this page. Height of the object over the focal length. The theta unaided is what we had on the previous page, which was height of the object over the near point. Good news, it doesn't matter how tall the object is, because what happens to the height of the object? Cancels out. And we get the angular magnification is equal to, I'll write this in long form, just so people can be comfortable with it. Invert and multiply when you divide fractions. So the angular magnification is your near point divided by the focal length of your lens. So once again, if your near point is 9 inches, did I do that right? If your near point is 9 inches, you're going to actually have a smaller magnification with this device because you were able to see a bigger angle to start with. If it's 25 inches, you'll have bigger magnification, but you'll actually be, in the end, the same size as somebody that has a different near point. So that's how we get the magnification of a single lens magnifier. What kind of lens was this? Was it converging or diverging? Converging. What would have happened if I changed it to a diverging lens? If I had it diverging, I put the object here, and I'm going to have, of course, my vertex ray goes like that still. I have these two focal points. The focal ray, well, let's do the parallel ray. The parallel ray goes like this and then comes out as if it came from that focal point, and it forms an image back here. And the focal ray would be going like this. So I'd have the image there. Is that a bigger or smaller image? It's smaller. It's also going to make a, yeah, it's not going to help me magnify anything. So that's why we don't use the diverging lens for a magnifier. We only use the converging lens for a magnifier. And notice you'd have to have this here as your near point where that image is. So you have to move it farther away. It makes it smaller. Doesn't help you. So you have to use a converging lens to make a simple magnifier. So that is the simple magnifier with the unaided or unaccommodated viewing. What difference does it make if it's accommodated? I'm not sure what the next question was, so I'm not going to go there until I go answer this question. If we go back to the picture I had drawn before, here's my optical axis. Here's my eyeball. Put the lens here. Put my image at the near point. then where's the object going to be formed? How do I find the object distance? It's what? Well, what's the general equation you use to find the object distance? That's right. 1 over focal length is equal to 1 over distance object plus 1 over distance image. Now we know here the distance image, I'm going to write something incorrect. Why is that incorrect? I didn't hear you, but I think you're right. Yeah, because my image is on the same side as the object and the same side that the object is. The lens is right here. It has to be a negative n. Is that what you said? We're assuming the lens is right on the eyeball. Okay, so the distance image is minus the near point. And so that means that the distance object is equal to 1 over f minus 1 over distance image is equal to 1 over f minus 1 over minus n, or 1 over f plus 1 over n. So that's how I calculate the distance object. Now that means that the angle that this is going to make for the vertex ray is going to be tangent theta is theta aided is equal to the opposite side, h0, divided by the adjacent side, which is d0. But 1 over d0 I just calculated. So I'm going to plug in that 1 over d0. So there's my angle for the aided viewing. So now if I want to calculate my magnification, aided, it should have said accommodated. I believe I have the right spelling, but if I don't, well, mock me in silence. So the aided angle is and the unaided is still this. Well, look at the second term. H odd over n divided by h odd over n, what is that? 1. So this turns out to be n over f plus 1. So the accommodated is n over f plus 1. You increase the magnification by a factor of 1. Now let's say you use a lens with a focal length of 2 inches, or 2 inches. It's centimeters, 25 centimeters is the has. And I've been saying inches all day long. Her near point was 9 centimeters, not 9 inches, right? Yeah. Okay, so 25 centimeters, I said 25 inches, I think, as well. So if we take that and we say, okay, your near point is the standard 25 centimeters, and the focal length is, let's say, 3 centimeters. 25 over 3 is 8 1/3. 8 1/3 plus 1 is 9 1/3. The difference between 8 1/3 and 9 1/3 is not a huge difference. So why would you want the eye strain for that small difference? So that's why we do our calculations based on, let's do it for the one without eye strain. So that's a simple magnifier. Any questions about the simple magnifier before I move to more complicated devices? No? Okay. If the object is placed at the focal point of the simple magnifier, where is the image produced by the simple magnifier? Just to making sure we were, on the page, listening. it couldn't take it. It won't. Okay. Okay, this is 11,360. Okay, we have a slight majority. So let's go straight to Gabriel. What was your answer and what was your reasoning?
So, answer B, and it was based on the thought process of the magnifier. If you're at the focal point, it should produce the same image at the focal point on the other side. But I'm saying that was an incorrect assumption.
It is incorrect. And I still have this. Let's just look at the answer. Since it's all still here. Except for what I'm going to do is, of course, run it backward. Because light works the same forward and backward. We're going to start with parallel rays, which presupposes the answer. And put the lens here. I forgot to turn off the lights. That was genius of me. So if I have my object here, the light goes out from the object in all directions, goes through the lens, and then where do the rays meet? Those rays are parallel. Where do parallel lines meet? Never. Right? So the answer is at infinity, which is our way of saying they never actually meet. So the answer to that one was, if we have the object at the focal point, then the image is at infinity because they never actually meet. And that was important to us because it allowed our eye to be relaxed, not straining to focus on something closer. Now, what you were thinking, the symmetry you were thinking, is 2F. If you have it 2 focal lengths away, it's okay because I have nothing of use yet. So if you have it 2 focal lengths away, then you're going to have an exact symmetry between your focal ray and your parallel ray. And so the image here, I don't know why I drew this second object, but the image would be 2 focal lengths away on the other side because of that symmetry. And that's actually how you get the closest image possible. If you're 2 focal lengths on one side, it'll be 2 focal lengths the other. If you're closer than 2 focal lengths but longer than 1, it will be farther than 2 focal lengths with the sum of the 2 being bigger than 4 focal lengths. So I'm guessing you must have played around or seen something to get that idea of the symmetry, but it's 2 focal lengths, not 1. Okay, so the correct answer here was the second most common answer, infinitely far away. On the same side, that is a point of preference. If they're parallel rays, they don't actually meet anywhere. You can say infinitely far on that side or infinitely far on that side, but if I'm looking this way, I can only see it on that side. And so that's why the answer is on the same side, because that's on the side you're looking. Okay, I don't know why I repeated this. It's not exactly the same. Let's go through a little problem and then go to telescopes. A converging lens with a focal length of 4 centimeters is used as a simple magnifier. The lens forms a virtual image at your near point, 25 centimeters from your eye. Where should the object be placed and what's the angle of magnification? I always tell you to start with a diagram. So here's my eyeball, and I have the lens here, and I have the image there. And what other information do we have? F is equal to 4.00 centimeters. And so it asks us, where's the object? So how would you answer the first part, where is the object? Okay, it's going to be in front, and Gila gave us the equation for doing that, right? 1 over focal length is equal to 1 over distance object plus 1 over distance image. So solve that for distance object. So my focal length, what's the distance image here? Negative, thank you. Negative 25, and it probably has a 0.0 centimeters, doesn't it? Yep. So 1 over 4 minus a negative 1 over 25, that's equal to 25 over 100 plus 4 over 100. So distance object is 100 centimeters divided by 29, which is?
3.45.
So the object is 3.45 centimeters away. It's like there for the object. So there's our first part of the problem. The second part is, what's the magnification? How do we find the magnification now? We can go through and recalculate everything, or we can just go with our equation. Magnification for accommodated was equal to n over f plus 1. So that's 25.0 centimeters over 4.00 centimeters plus 1. So 25 over 4 is 6.25. Add 1, 7.25. And we put a little x there for times. So the angular magnification is 7.25 times. That means the size of the things we see are 7.25 times bigger angles with this simple magnifier. So the math, not complicated at all. The derivation, a little more complicated. The understanding which type of lens and why you use that lens, the important things. What's the point of a compound microscope? Now, this is a question I haven't lectured on. It's asking your preconceived notion. All right. We had pretty strong agreement. So I'm not going to ask questions here. I'm just going to go on and explain micro. Micro means small. So the point of a microscope is to focus on a small thing. Now, if it's a small thing, assumedly we can manipulate its position. And just like with a simple magnifier, we're going to bring that thing closer so we have a bigger angle it can make. So a microscope is specifically designed to magnify small things that are nearby. Large objects, micro means small, so not that. Small objects that are far away. Well, a microscope in theory, I suppose, could be used for something small away, or far away, but you're still not going to be able to see much if it's small. And the word tele means far. So a telescope is designed for looking at things that are far away. So a telescope is looking at things that make a small angular size that are far away. But of course, if it's far away and makes a small angular size, it's probably still large. So telescopes are used for looking at large things that are far away. Microscopes, small things that are near. Okay, so let's look at the compound microscope. That's a compound microscope. Got it? Excellent. Okay, let's work with the simple things of how a compound microscope works. You have two lenses now. That's the compound part. The first lens, the one that's close to the object, we call the objective. And the point of the objective is to magnify as much as you can. Then you have the eyepiece, the one that's close to the eyeball, and the eyepiece is going to create an image that you can focus on far away from that magnified image. So the eyepiece is going to be actually the same as a simple magnifier. So we break our magnification equation up into two pieces. We have magnification of the eyepiece is equal to, and if it's unaccommodated, it's going to be the same as what we saw in our previous work. Now notice this picture has a distance image prime. If it's unaccommodated, what is that distance image prime? Where are you looking at if it's unaccommodated here? The far point. The far point, which for the normal eye is infinity. So for the unaccommodated eye, this distance image prime is infinitely far away. So your eyeball is relaxed. So we have the magnification of eyepiece, and then we're going to have the magnification of the objective is the height of the image from the objective divided by the height of the object for the objective. Notice the terminology here. There's no prime for height image if it's the image of the objective. And that height of the image becomes the object, well, the image from the objective becomes the object for the eyepiece. So we have, anytime we have a compound situation where we have more than one lens, the first lens, you just calculate what it's going to do and where its image is. And then that image from the first lens becomes the object for the second lens. And so that thing I circled there, the HI, the image from the first lens, from the objective lens, is also the object for the eyepiece. So since that's the object for the eyepiece, if I am doing unaccommodated viewing with my image infinitely far away, where's the object for the eyepiece going to have to be located? At the focal length. At the focal length of the eyepiece, I was going to call on Gabriel because I had him explain this one. We have the clicker question. If the object is at the focal length of the lens, then the image is infinitely far away. So that means that we're going to have this distance object prime is equal to the focal length of the eyepiece. That's a given if it's unaccommodated viewing. Okay, this image here is the first image. This image here is the one we're looking at. Because, okay, you have the first lens. So the first lens is just, here's my objective. Here's the object. And here's the image. So that's my first lens. And so, as always, we can do ray construction, parallel ray through the focal point. Okay, so I clearly randomly didn't choose something that's going to be correct, but that's because I drew random lines. And this one here should go like this, right? So based on what I drew, it should have the image out there. Let's just go with the first picture and not worry about those distances being correct. So that's what's going on with the first lens. And so where it says HI, that's this right here. But then the second lens is taking that same HI, putting it focal length of the eyepiece away from the eyepiece, and then forming the HI prime out here. So we have two pieces to analyze. What's going on with the objective and what's going on with the eyepiece. But since the eyepiece is just a simple magnifier, I went straight to the result for this eyepiece. Okay, I've got to erase that because you have to be able to see the difference in focal length sub E for eyepiece and focal length sub O for objective. So I went straight to the magnification of the eyepiece because it's what we've already done. But then we still have to do the objectives work. So now we're focusing on this picture here and trying to find what the relationship is for the magnification of that one. So the magnification is going to be this height of the image divided by the height of the object. But we learned another equation for that, an equivalence. What was the equivalence we learned for the magnification based on geometry? Based on the vertex ray and the principal axis. I'll draw the two. Okay, this angle here and this angle are the same. So they have the same tangent, which means that you have the HI over DI is equal to HO over DO. But there's a minus sign because it's inverted, so minus distance image over distance object. Well, from the work we've already done 2 times, we know that this is equal to minus distance image times 1 over distance object, which was 1 over the focal length minus 1 over the distance image. So that's one way of writing it. So there's the magnification of my objective. So if I want the total magnification is going to be the product of these two. So magnification total is magnification of the eyepiece times magnification of the objective. I should have been clear here. That's focal length of the objective there. And so that's going to be now, nobody likes to leave it like that. We like to at least get a common denominator in that thing that I put in the brackets. So I think it's clear. What would the common denominator be? Yeah, focal length of the objective. So this is equal to, I'm going to bring out a minus sign, N over FE, FO, and then the thing in the brackets, since I multiplied the second one by FO and changed the signs, it's that. Now that's correct, but we usually go one step further. Because where is that distance image? I don't know, but it depends on the length between my 2 lenses. So if we look at the length between the 2 lenses, if I call this the length is distance image plus that distance object prime. But what was the distance object prime? Focal length of the eyepiece. And so that means the length of my microscope is equal to distance image plus focal length of the eyepiece. Hence, distance image is equal to length minus focal length of the eyepiece. Substitute that in here, and I have the most common form of this equation. And I ran out of space. Makes me proud. So it's minus n, the near point of the eye, over the product of the 2 lenses, and then times the separation between the 2 lenses minus the 2 focal lengths. It's not overly complicated if you think about it, but it took a little more work to get there. Notice something interesting. according to this equation, it shouldn't matter if you replace the two lenses, if you turn a microscope backward. How do people turn a microscope backward? You guys, one, man after my own heart. When I was a kid, I had to see what's it like. Does it? Well, it didn't work very well. It doesn't magnify. Why? Because you have different focal lengths of the two lenses depending on their goals. You want a very, very short focal length for the objective so you can get the object very close to the objective. And because of that, it turns out that the separation of the two lenses is going to be very different if you change the direction. And so you have to change the separation of them. And as D changes, so is your magnification. So you don't get good magnification if you reverse it. So even though the equation looks like it doesn't matter which lens is the objective and which one is the eyepiece, it does. You want that really short focal length lens to be the objective. So now, practical experience. Do you guys use microscopes in like your biology class? So when you're using the microscope, how do you adjust the focus? You do what?
You bring it closer or farther away.
Okay, you bring the sample closer and farther away? So if you're bringing the sample closer and farther away, which of the parameters that we've been talking about are you actually adjusting? You're adjusting the distance objective, right? The distance it is away. Now there's another way that you could adjust the focus, and that would be adjusting the length, the separation between the two lenses. Both of those would adjust the focus, the magnification. And so ideally, you would like to have the object real close to the focal length, but not at the focal length because it won't work, of the objective, and then have that barrel the length that matches. So you can actually adjust the length of the barrel and then have to move the object to a different position and it'd be in focus again. And then that equation will tell you what the magnification is for that arrangement. If you want to go to higher and lower magnifications, what do you change? You usually just change the objective. The objective is your primary magnifier for the microscope. You change that objective to something with a shorter focal length. If it has a shorter focal length, what's it doing to the equation that I shall put in a red box? What's it doing to this equation? Perfect. There. What's it doing to that equation if you make the focal length of the eyepiece smaller? Yeah. You divide it by a smaller number and it becomes bigger. Now there's a minus sign in front of that. What does the minus sign mean? It's inverted. So if something's on the right side of your viewing angle, you have to adjust the microscope slide and slide it to the right to move it toward the left in your viewing because of that minus sign. So that's our microscope. And oh goodness, got 1 minute left. We're clearly not going to cover telescopes in 1 minute. The numerical aperture is a measurement of the acceptance angle. That is, light comes from your object and it goes out in all directions. If you can get closer, you'll get a higher percentage of the light. So that acceptance angle, the numerical aperture, is basically telling you what percentage of the light you're getting. How can we improve that? Well, if we can bring them closer together, we can improve it. And we do that by putting a liquid in there. We put something like water between our sample and the objective. And because there's water there, you have a shorter wavelength, right? Slower speed, so shorter wavelength. And thus, we can actually bring it closer. And that allows us to have a better numerical aperture, allow more light in.